Hello everyone and welcome to today's lecture. So today I'll be going over a number of different examples that are related to the last lecture, and the motivation here is twofold. It's both to see how many different problems in mechanics can be modeled using systems of ordinary differential equations, some nonlinear, some linear, depending on the assumptions that we're making in the model. The other main goal of today's lecture is to introduce a concept from mechanics called Lagrangian mechanics. And along with that, I'll also introduce a topic called Hamiltonian mechanics. And in some sense, these two different ideas in mechanics are going to give us a very general method for obtaining the equations of motion for a given physical system, the true equations of motion of the system. And both of these methods can be used and extended. The ideas from them can be used and extended to study general dynamical systems, or general systems of nonlinear differential equations, independently from the physics that the idea is coming from, which is very cool. Both of which are actually very advanced topics in what's called the calculus of variations, which I'll provide a reference with when we get to that part of the lecture. So basically, for today's lecture, what we're going to want to be considering is, and we'll start off by considering the SpringMass System. Specifically, we'll consider how to correctly derive the equations of motion for the SpringMass System, and we'll see that by the end of the lecture today, we're going to have two general methods for deriving the equations of motion for really any physical system, but the SpringMass System is a great place to start with. So let's draw a diagram. We're going to assume that we have a spring connected to some mass m. That's in motion in one dimension on the x-axis. We'll call x of t the displacement of that mass from the equilibrium position of the mass. And first here we're going to make a couple assumptions to help us along. We'll assume that the mass m is constant. We'll assume no friction. So no air resistance, or resistance due to the whatever surface the mass is sliding on. And we're going to assume no external forces. So we're not going to place any external forces on the mass. And hopefully this is an example that you've seen before in your ordinary differential equations class. But even if you haven't, it's okay. The main thing that we're going to use here is Newton's second law. To derive the equation of the motion of this mass. And Newton's second law says that for a mechanical body, the net force vector on the body, which is the sum of all forces acting on the body, will be equal to the time derivative of the momentum, which is the mass of the body times the velocity of the body. And this is where our first assumption comes into play here. We're assuming the mass is constant. So if the mass is constant, this is just going to be m times dv dt. Or if the velocity vector we think of as the derivative, time derivative of the displacement vector, this is saying that this is m times the second derivative of displacement with respect to time. And if there's no external forces and no friction, then the only force acting on the mass is the force of the spring. So this net force vector is just going to be the force vector of the spring force. And our first modeling question here is going to be, well, what is this spring force vector? Or what's the force of the spring acting on a given mass? And to answer this question, one might take a given spring and do a number of different experiments on it to get some sort of experimental relationship that you can then use in a model. But typically, a tension curve or a tension displacement curve looks like something like this. Where on the x-axis here we have the displacement of the spring, and on the y-axis we have the tension in the spring. And the idea here is that if you have the x is positive, right, you're going to have a positive tension in the spring, and if the x is negative, you should have negative tension in the spring or compression in the spring. So I want to point out here that this curve is nonlinear in general. But for a very small region, say from right here to right here, the curve is approximately linear. And this is the region where the spring is called Hookean, or where Hooke's law dominates. And for such a string, we have the restoring force is very nice. So I want to say here, in general, the restoring force on the spring is nonlinear. In general, this F spring force vector is going to be equal to some nonlinear function of the displacement vector multiplied by negative times the direction of the displacement vector. This is just the magnitude of the spring force. And this is the direction of the spring force. If the displacement vector, the size of the displacement vector is small enough, I should say is small enough and stays small enough, Hooke's law applies. Which means that this is when f of the displacement vector for the magnitude of the spring force is equal to k times the length of the displacement. This k times the size of the displacement. And it's important to point out that this is valid only if the deflection is small enough. But from this, if we assume that it is small enough and Hooke's law does apply, then from Newton's second law, we get that the spring force is, in our notation, negative k times x I hat. The I hat is the x direction. And this is going to be equal to m times dv dt I hat, which gives us, if we express dv dt in terms of x, is v, we're assuming is the x velocity because we only have one velocity component, and this is going to be d squared x dt squared. We get the differential equation, negative kx is equal to m times dx dt, or the equation or sorry, d squared x dt squared. So the equation m d squared x dt squared, the second derivative of x with respect to time, plus k times x is equal to 0. And this is a second order linear ODE. Which should be familiar from your ODEs course. This is probably one of the first second order ODEs that you went through and learned how to solve. And in terms of what we're going to be talking about and what we talked about in the last lecture, I want to emphasize that this single second order linear ordinary differential equation is equivalent to the following autonomous system of differential equations. If we define xi, the vector xi, to be the vector xv, then the derivative of xi is equal to x dot v dot and this equation is the same thing as m times v dot is equal to negative k over mx. Then x dot is equal to v by definition, and then v dot is equal to negative k over mx. So v dot is negative k over mx, which is just a function, a vector function of all of the things in xi, all the variables in xi. So this system of differential equations, which I'm just going to box right here, is a first order autonomous, or I'll say autonomous first order system linear system of ODEs. And it's a system of two ODEs. So this is very cool, and everyone should hopefully go through and know how to solve such a linear system of ODEs. You want to go through and practice that, but the idea is that we're going to gradually complexify our understanding here as we consider more and more complicated examples. But using the techniques that we've developed so far, we can look at this and say, well, the equilibrium points are going to be when v equals 0 and negative k over mx is equal to 0, which means that this is going to be an equilibrium point when v is 0 and x is 0. Always. So we always have one equilibrium point. And then not only that, we can go through and use the implicit function theorem, which guarantees that when the derivative of x is non-zero, that dv dx is going to be dv dt over dx dt. So this is solving for the shape of solutions in the phase plane. And this will be negative k over mx over v. So any phase curve or orbit in the phase plane will satisfy this single differential equation, which ends up being the same thing as if we integrate both sides with respect to x. It's the integral of v, when you multiply by v dv is equal to the antiderivative of negative k over m x dx. So v squared over 2 should be equal to negative k over m x squared over 2 plus some constant of integration c. And we can rewrite this as v squared plus k over m x squared is equal to 2 times c, which, because c is an arbitrary constant, we'll just rename that as d. And this is exactly the equation of an ellipse in two-dimensional Vx space. The idea is that these curves are so for the differential equation system that we just wrote down, this is the form of the solution curves in phase space. And these are ellipses. You can kind of see this a little bit better if you take d and you divide by d. So you'll get v over the square root of d squared plus x over the square root of d square root of m over k squared is equal to 1. This might allow you to see that this is going to be an ellipse in this space a little bit better. That this equation is equivalent to the one that is written right here. So these are ellipses with a semi-major axis and a semi-minor axis coming from these values right here. So remember the equation of ellipse is v over b squared plus x over a squared is equal to 1. Let's take a look at what some solutions look like, and I'll really just do two different initial conditions for one values of parameter. We'll do k equals 1 and m equals 2. So if we use the Python code that we use for the local Latera system, we see that this is the solution for two separate initial conditions. Xi1 initial condition 1, which is at 1, initial spring displacement of 1, and Xi1 is, or Xi2, Xi1 for IC1 is 3 right here. So we have two separate initial conditions, and the initial velocities here are these two values. We're going to start with just an initial velocity of 0 for each of these. And you see that you get this nice oscillation that you would expect from the exact solution. And sure enough, if you plot out the exact solution on here, it would very, very exactly match these curves. These are numerical computations, but we can go through and solve this system using methods that we know from our previous ODE course. We can also plot out these curves, these ellipses in phase space, and plot out numerical trajectories in phase space using the code from before. And when we do this, we get a picture that looks like this. Which is exactly what we would expect. We have a whole bunch of the exact solution here is plotted out as these curves that are dotted in dash. And the approximate solution, or the numerical solution, is the solid lines here. These are colored according to where we start. You see that here, you start here, you end here. This trajectory, you start at this initial condition, you end up going here. So we see that the phase flow for our chosen values of the parameters. Right, the orbits are moving around phase space like this. And this is the critical point that we calculated before as well. So you can see that this is a stable but not asymptotically stable critical point because for any epsilon that you surround that critical point, there will exist a delta that you can surround the critical point, for which the solution with initial conditions inside the delta region will stay inside epsilon for all t. But it is not asymptotically stable because the solutions are not converging to that equilibrium point. So now let's focus on some extensions. We want to see, before we said in general, the force of the spring depends on displacement in a nonlinear manner. So we'll do extension 1. We'll see there will be a number of different ways of extending this. Well, you go and you look back at that force picture, the tension picture, a function that maybe better models the force of the spring would be a cubic function. In which case the force of the spring be equal to some constant k3 times x cubed times negative I hat. And when you plug this into the Newton's second law from before and get a differential equation, the resulting differential equation that you get is m x dot dot is equal to negative k3x cubed, or ultimately k3x cubed equals 0. And this is a nonlinear. Second order ODE. Using the same idea as before, the velocity is the derivative of x. And this equation is the same thing as mv dot is equal to negative k3x cubed. So with xi is the same as before, we have that xi dot, which is just the vector x dot v dot is equal to v negative k3 over m x cubed. And this is some vector function of just xi and xi alone. And this model is a better model for a spring because it takes into account a more realistic assumption of the spring force. And it depends more realistically in terms of x. Now, again, for large values, very large values of x, it's not going to be super realistic because it's not going to accurately describe what's going on with the relationship between the spring force and the displacement. But it's definitely better than the linear assumption. And this is an autonomous system as well. Nonlinear first order ODEs. We still have equilibrium points that we can go through and calculate. This has equilibrium points when v is 0 and negative k3 over m x cubed is equal to 0. So when x equals 0, so we have another equilibrium point at the origin, but the characteristic, shape of the solutions in phase space are going to be different. So any orbit in phase space, again, we can go through and calculate dv dx when x dot is non-zero will be v dot over x dot, which will be negative k3 over m x cubed divided by v, which is a separable ODE, so we can go through and integrate it to get the integral of v dv is equal to the integral of negative k3 over m x cubed, which is the equation v squared over 2 is equal to negative k3 over m x to the 4th over 4. plus c, which is the same thing as the equation v squared over, or b squared plus k3 over 2m x to the fourth is equal to 2 times c, or we'll just call that d. So this is a new curve. It's expressed as a level curve. Basically, the level curves of this function for any value of d is going to be a curve in phase space of this autonomous system of differential equations. It's an orbit in phase space. So let's take a look at what the dynamics of such a spring are going to look like. And we'll use the parameters m equals 1 and k3 equals 0.25. All of the plots that I'm going to show in the lecture can be made using the Python program that we talked about in class with suitable modifications. So you have to make sure you modify correctly and change the system of differential equations that you're solving, as well as possibly the initial conditions and the parameters as well. But for these two parameter values, this is what it looks like, or I should say the displacement of a spring with a cubic force function for the spring force looks like. So you have this, it's like definitely a change between the previous plot, going from time of t equals 0 to time of 17.5, you get through 2 oscillations. Here we get through almost 2.5 oscillations for these parameter values, and you notice that there's almost a region with the velocity is almost constant. It looks like it is constant for certain values right here. And for smaller initial conditions, right, it takes longer for the spring to oscillate back and forth. The orange curve here, the first larger curve, corresponds to the spring displacement for a larger initial condition than the blue curve. So if we go through and take a look at this in phase space, there are multiple different solutions here in phase space, along with those level curves that I talked about before and that we went through and solved for. So this is a picture of what the phase space looks like. By the way, on all of these phase curves, I plot the initial condition, both initial conditions. One and 3 that are done in the previous plot, so you can see what these two trajectories look like in phase space. So this is initial condition 3 right here, and this is initial condition of 1. This is really neat because you're seeing exactly the exact solution that we found is matching completely with the correct, the numerical calculation, and the behavior that you're seeing here of the solution is directly related to the shape of the curve and how fast you're moving around the curve for different initial conditions. So let's see another example, and we'll kind of extend the model a little bit more. And this also has to do with the spring force. So when I stick with the spring force, we're going to consider what's often a very accurate model in reality. We're going to consider a combination. The cubic and linear force laws, or restoring force, from before. And this gives us a spring force of kx plus k3x cubed. This is, and remember, times negative I hat, because for the specific scenario that we're interested in here, the direction of the spring force is just along the x-axis. So when we plug this into Newton's law, we get the differential equation m times the acceleration, second derivative of x, is equal to negative k times x minus k3 times x cubed, which is m times x double dot plus kx plus k3 x cubed equals 0. This is a single second order nonlinear ordinary differential equation that, using the exact same process we talked about before, can be rewritten as xi dot, which is x dot y dot is equal to v, is x dot is equal to v, and then y dot will be equal to negative k over m x minus k3 over m x cubed. And this is a vector function of variable xi. So this system is an equivalent system to this second order nonlinear ODE, but this is now a system, or autonomous system, of nonlinear first order ODEs. And this has equilibrium points when v is equal to 0 and This combination right here is equal to 0. So we can factor out a little bit and re-express this a little bit nice, a little bit more nice. If I factor out negative k over mx, this is negative k over mx times 1 plus k3 over k times x squared is equal to 0. And this equation now has more than one solution. This has a solution. X is equal to 0, or when x squared is equal to negative k over k3. Which you may say might not be possible, but it actually is possible to have this equation satisfied. K is always going to be positive, so this will only be satisfied if k3 is negative. And this presents a very, very interesting bifurcation for us. We actually have now a bifurcation in the parameter k3, because if we assume k is positive, then when k3 goes from negative to positive, when it's negative, we have 3 equilibrium points. The equilibrium points are 0, 0, negative absolute value of the square root, negative square root of the absolute value of k over k3, comma 0, and positive is square root but when k3 is greater than 0, we only have one equilibrium point. And what's neat here is that regardless of this bifurcation, this differential equation that we get when we go through, we get the phase plane solution, or the phase plane solution for the orbits. Is going to be that dv dx v dot over x dot. This is when x dot is non-zero. Will be negative k over mx minus k3 over mx cubed over v, which is the separable ODE. And don't be fooled. I've chosen these examples very carefully. They're not all going to be separable ODEs, and when they're not separable ODEs, things can sometimes get a little bit tricky. You can get very, very complicated differential equations for orbits, but these are all very nice examples that we've seen so far. This now becomes the integral v dv. This has to be equal to the integral of negative k over mx minus k3 over mx cubed which gives us v squared over 2 is equal to negative k x squared over m times 2 minus k3 x to the 4 over m times 4 plus some constant c, which can be rewritten as v squared plus k over m times x squared plus k3 over 2m times x to the 4th plus c. And there you have it. These are level curves, and so these level curves are exact solutions for orbits in the phase plane. For this autonomous system of nonlinear first order ODEs. So when you're doing this, you can just really use any plotting program that you have use of. I recommend using Desmos, and this should be an equal sign right here. So sorry, and we'll also change this to D just to not confuse. It'll be multiplication by 2. But so you can use Desmos to very nicely get a plot and a visualization of these level curves, which are the orbits in the phase plane. Now, I want to emphasize here that we have two bifurcations for K3, two possible values for K3, and each of these possible values for K3 represent different things physically. And the first possibility, or the first bifurcation for K3, is that of what's called a soft spring. This is K3 less than 0, or negative. And the reason that this situation is called having a soft spring is because a soft spring, or call a spring soft, if it's a spring that is easier to stretch and compress than what we would get with Hooke's law. And to get a visualization of this, I recommend opening up Desmos and kind of plotting out the function kx plus kx cubed along with the function y equals kx. And this function is going to look like this. So if this is the tension function of the spring, then Hooke's law is just the linear relationship y equals kx. And if we have the relationship kx plus k3x cubed for a negative value of k3, you notice that any given point, say right here, the value of the tension is less than the value that you would get from Hooke's law. Same thing for our compression. Look at this right here. The value of compression here is of a lesser magnitude than the value from Hooke's law. So this is why we call negative K3 a soft spring. And you want to be very, very careful here, because just like how Hooke's law is only valid in a certain region, right, where the function is very close to linear, we don't want to go too far with our initial conditions here. Right? We have, we call this point A and this point B. Past a certain point, solutions are non-physical. Right? In reality, the spring constant isn't going to go up to a value here and then drop down to negative values for large enough displacements. Same thing here. So for at least a standard SpringMass system or SpringMass example, so you want to be very, very careful when taking something like this and looking at solutions in the phase plane. You can still study the dynamics of such a system, but it is very, very important to take this into note. So we've defined a soft spring and defined a hard spring now. And I think with the understanding of soft spring, it'll be very, very clear. A hard spring is just more difficult to stretch than Hooke's law. Stretch or compress. And just like before, you got a nice plot that I made in Desmos to visualize this. So we have a plot of the function kx plus k3x cubed for k equals 1, k3 equals 0.5. And you see that for any given value, the tension is greater than what it would be with Hooke's law. And same thing right here. So the compression is a larger magnitude than what you would get from Hooke's law. So let's look at this first in terms of the effects on the solution. This is for it's a soft spring. For K3 is equal to negative 0.025, K1 equals 1, and M equals 1. And we see some really nice behavior here in terms of the solution. It's not very abnormal, but it is a little bit different for different initial conditions. And sure enough, if we take this and we look at this in the phase plane, we see that exactly what we expect from a function of the form kx plus k3x cubed for small values of x and v, the velocity for small initial conditions. We have that. These level curves, the dotted lines here, are the exact solution with the numerical solution plotted on top. And you see that for small values, you're getting approximately linear results, which are circles. But as you increase the size, you get, or of the initial condition, you get increasingly bizarre, or I shouldn't say bizarre, but different behavior. It's kind of bowed out circle as you get larger and larger and larger. And like I mentioned before, you got to be very careful that you don't go too large, because if you do go too large with your initial conditions, you run into something like this. This is what happens. So you'll remember that for a soft spring, when K3 is negative, we found 3 equilibrium points. And middle equilibrium point at 0, 0 is stable. But if you start with an initial condition that's too large, what ends up happening with the dynamical system is that the trajectories in phase space end up shooting around, and actually these are both unstable equilibrium points, so that the trajectories shoot off in this direction right here, and correspondingly in this direction right here. And these correspond to a non-physical solution to our system. It's when this function right here ends up being negative and positive right here. So the idea here is that you want to be very careful with your model and the bounds of your model and where your initial conditions are, because you can always study the dynamics of a different system of differential equations, but you got to be very, very careful on whether or not the solutions of that system are accurately describing reality or not, and whether or not you have physical or non-physical results. So for the hard spring, we have a result that looks like before. And really, it looks kind of like a combination of the purely linear case and the positive value of k, for the purely cubic case. It's kind of like a nice little combination of both of them. Sure enough, if we look at the phase plane diagram for this case, this is the picture that we get right here. And this is a nicer model, because you see that for small values of initial conditions, you're getting circles, or what look like circles in the scaling, but can very well be ellipses. But for larger values of initial condition, you're getting the characteristic behavior of the cubics and the spring in the phase space. These are the exact solutions, again, plotted with the numerical solutions. So you can see that it's an exact solution, and the numerical results here are exactly predicting what's really going on.